What's up, everybody? Today we're going to be continuing graphing polar equations, and I want to start off today by just reviewing our symmetry rules for polar equations of the form r equals. When you have sine of theta somewhere on the other side of r equals, that means your graph should be symmetric with the line theta equals pi over 2, which is a lot like the y-axis. They're one and the same. And if it would include cosine of theta on the opposite side of r equals, then your graph should be symmetric with the polar axis, which is theta equals 0, or the x-axis, okay? So keep those symmetry rules in mind as we go through our examples today. Now, we're going to be graphing what are referred to as cardioids and limosons today. There's 3 different types of graphs, and they all will follow, their equations will follow the same format. They all will look like r equals a number a plus or minus a number b multiplied by sine or cosine of theta, okay? And which type of graph you end up with depends on how the value of a and b compare to one another. So when a and b are the same value, you'll end up with a cardioid, and a cardioid will always pass through the pole, okay? If you have the a value larger than the b value, you will end up with what's known as a limason that has no loop. Sometimes it's referred to as a dimpled limason. These look a lot like cardioids, except they don't pass through the pole, okay? And lastly, if you switch it and you make a smaller than b, you're going to end up with a limason that has an inner loop. And big idea behind this graph is when you sketch it out, you're going to have to pass through the pole twice. So let's illustrate each one of these for you. I'm going to use the GeoGebra link here. All right, and in this particular applet, it uses the letter T, okay? And T represents your angle measure, okay? So I'm going to graph the equation r equals, let's just do 2 plus 2 sine of t, okay? Notice both the a and the b value here, they are the same number of 2. So this is going to result in what's referred to as a cardioid. Starts out at t equals 0 and just, rotates around, keeps increasing the value of t. It's in radians, and you can see that it sketches out the corresponding point for the r, based on the r value. So this is what a typical cardioid looks like, okay? Notice how it does include a point at the pole, okay? Now let's reset this. And now I'm going to make the a value bigger than the b value. So let's make a 3. And this should result in a limason, sometimes referred to as a dimpled limason. And you'll see it starts off looking very similar to the cardioid. Just notice right about here, there's the little dimple. Notice it just doesn't pass through the pole, okay? All right, so that is a limason with no inner loop. Let me pause that, and now let's reverse it. I'm going to make A2. Actually, I'm going to reset first. Let's make A2 and B3. Okay. This should give us the inner loop. So once again, starts off pretty similar to the other two. And notice once we get down here, I pass through the pole, loop around, pass through the pole again. There is your limason with an inner loop. Okay. All right, let's go back, and we're going to graph some of these ourselves now. You will see that I already have some tables of values drawn out here. Reason for that is just to kind of speed up this video a little bit for us. Okay, so notice the equation we're trying to graph. R equals 2 plus 2 cosine of theta. Notice my A value is 2, so is my B value. So the fact that A equals B, that tells me I have a cardioid for the graph. Okay. Notice this is an equation that involves cosine, so I want to reason out that there should be symmetry on this graph with theta equals 0, which is the polar axis, and I'm going to draw in a dashed line there to help me remember that. All right, now, it's pretty simple to graph these. Basically, you can just plug in any value you want for theta, and then you'll get a corresponding R value, and you plot the point that's associated with that. The more points you plot, the better your picture is going to be to represent your graph. I would say at the very least, you should be plugging in the quadrantals for theta as well as multiples of 45 degrees. Okay. Now notice in my table here what values I chose for theta. So I chose 0 degrees, 45 degrees, 90 degrees, 135, and 180. So 0, 90, and 180, those are all quadrantals. And then 45 and 135, those are multiples of 45 degrees. Okay. Notice I didn't plug anything beyond 180 degrees in. That's because of this idea of symmetry across theta equals 0. I'm not going to need to plug any larger angle measures than 180 in if I understand this rule of symmetry. Okay, so let's go ahead and plot each one of these. So if I put 0 in for theta, make sure your calculator, if you're doing this yourself, make sure your calculator's in the right mode. You'd want to be in degree mode here. So 2 plus 2 times cosine of 0 degrees should give you an R value of 4. So to plot the point, that would be 4, 0. I'd end up right here. Okay. If I plugged in 45 degrees, 2 plus 2 times cosine of 45, that would be an R value of approximately 3.4. So sweep out your 45 degrees and then count on the terminal side of that almost 3.5 units. That places you right about here. And then here's where we can use our symmetry. Reflect that across theta equals 0, and you'll end up with another point right here, which we can think of that as a theta value of 315 degrees. Okay. Cosine of 90 is 0. 0 times 2 is 0. 0 plus another 2 is an R value of 2. So if I plot the point 290, end up right here. Reflect. Gives you another point. Plugging in 135, notice the R value is approximately 0.6. So sweep out your 135. That takes you into what would be the second quadrant, in the rectangular coordinate system. And that's going to put you right about there. Reflect across that line of theta equals 0. Get you another point. And then plot your last one. When I plug 180 in for theta, I end up with 0 for R. That's my pole. Okay, now it's time to just sketch this out. I'll start at the first point of 4, 0. And I just come around here, go into the pole, and there we go. That's not the greatest. Let me do that again. Looks a little better. All right, so there's your cardioid. Okay, next I want you to make a couple observations here notice that the distance from the pole out to this furthest point here, that is 4 units, okay, which is the sum of A and B. And then this distance from the pole to that point right there, that is 2 units, which is your value of A, okay? Keep that in mind as we move through some of our other examples here. All right, moving on to example 3. Equation we're trying to graph here is R equals -3 plus 2 sine of theta. Okay, now when I make a comparison between my A and my B value, I'm gonna take the absolute value of A. Okay, so my A value I want to think of as 3 here. Okay, A is 3. And then my B value is 2. So of course A is larger than B here. Okay, and we'll see in the end after we plot all of our points how that negative in front of the 3 actually affects the graph here. Okay, notice the equation has sine of theta in it, so my symmetry here is going to be at theta equals pi over 2. Let's draw that line in. And then notice I've labeled this is going to be a limosol that doesn't have a loop because of the fact that the A value is greater than the B value. All right. Now notice the values that I've chosen for theta this time. So I chose 0, 45, and 90. That would span from the positive x-axis to the positive y-axis. But then I also chose 315 degrees, or you could think of it as -45, it doesn't really matter. And I chose 270 or -90. So notice every single angle measure that I chose here for theta, it's on the right side of my line of symmetry, okay? Similarly, if you went back to this previous example, you notice all the angle measures that I chose for theta here, they were all above my line of symmetry. Okay, I don't need to pick values where some are on one half the line of symmetry and others are on the other half. Okay, so that's the reasoning behind what I chose here. When I plug in 0 for theta, I end up with -3 for R. Okay, so here you have to be very careful with how you handle the R value that's negative. Okay, so you'd sweep out your theta degrees. In this case, it's 0. That will put you on the polar axis, right? If R is negative, you actually have to go in the opposite direction. So that's going to be at this point right here. Okay. And if I plug 45 degrees in, I end up with R being approximately -1.6. So you sweep out 45 and go in the opposite direction from that terminal side, 1.6. So that's actually going to take you this way, which would be more like the terminal side of, that would be 225 degrees. Now you can reflect that across your line of symmetry right here. Okay, if I did 90 degrees, plug that in, I end up with -1. So sweep out your 90 degrees. R value of -1 takes you in the opposite direction, places you here right on the line of symmetry. Okay. If I plugged in 315, I end up with R equals -4.4. So you sweep out your 315. Initially, that puts you in what's like quadrant 4. Go in the opposite direction, though, 4.4. And that places you right about here. Just estimate it. And then reflect across that line of symmetry. And lastly, if I plugged in 270 degrees or -90, I should end up with a R value of -5. So sweep out your 270, go 5 units onto the opposite side of that terminal angle. It places you right here. And just now realizing I never reflected my initial point, I should have another right here as well. Okay, so now we can trace this out. I'll just start on the polar axis. We come up, come around, and there you go. There is your limacon without a loop. Again, sometimes referred to as a dimpled limacon. All right, now once again, want you to notice the distance from the pole to this high point here. This is 5 units, which is the sum of your A and your B value. And then the distance from the pole out to here is 3 units, which is the same as your A value. Okay. Also, one more thing we can mention, we didn't need to focus on this with the cardioid, but if you look at the distance from the pole down to where the dimple takes place, that's 1 unit, which is the difference between the A and the B value. Okay. All right, last example here. Here my A value is 2. Choose a different color. So A is 2, B is 3. Notice that A is less than B here, so in this situation we'll end up with a loop, limacon with a loop. All right. And we're back to having cosine in the equation, so my symmetry is going to go back to theta equals 0. And that means I can use the same angle measures that I did back in the example with the cardioid. Okay, so 0, 45, 90, 135, and 180. If we plug 0 in, I end up with an R value of 5. Notice that's right on the line of symmetry. If I plug 45 in, I end up with 4.1. Reflect it. If I plug 90 in, I end up with 2. Go ahead and reflect it. And then here's what will then allow for the loop. Okay, notice when I plug 135 degrees in, I end up with an R value of negative 0.1. So you sweep out the 135, go 0.1 units on the opposite side of the terminal angle in the opposite direction. So let me zoom in here. That's going to place us right in there. Okay, and then we reflect. All right, both of those points are pretty close to the pole. All right, and then one more to plug in. If I did 180 degrees, I end up with an R value of negative 1. So you sweep out the 180, go 1 unit off the opposite direction of the terminal. That's going to put you right here. Okay, now we can sketch this out. Starting at the positive polar axis. And there is my limacon with a inner loop. Once again, we want to notice distance here is 5 units, which is the sum of my A and my B value. Distance here is 2 units, which is the same as my A value. And then the length of the loop is 1 unit, which is the difference between my A and my B value. Okay, so very similar observations to the last 2 examples. All right.